Swayamprabha. Digital India. Educated India.
So far we have discussed about various applications of microfluidics, and now we shall proceed into the theoretical description of the subject to understand better that how a basic theoretical building block or how a basic theoretical foundation can be used to solve problems in microfluidics. While mentioning that, it is also important to appreciate that always continuum hypothesis may not work for applications over small scales, but there is a wide class of problems where continuum hypothesis will still work with certain modified considerations. Therefore, I mean we will try to begin with the continuum considerations. One of the big issues that we would keep in mind is that like these conservation equations are fundamental to even macro scale flows. So, but in micro scale flows there may be certain alterations, but before understanding the alterations we will revisit the governing equations and their derivations. Now for the remaining part of this course I will try to follow a teaching methodology which is a somewhat hybrid type of teaching methodology. So what we will do is we will describe the derivations, of course in the forms of slides to make this video lecture more effective, but at the same time we will work out some of the key steps in details in the board. So we will use a mixed mode of demonstration, and I believe it will be interesting and useful to you. It is neither the classical old style of presentation where the entire thing is done in a board, nor the seminar type of representation where the entire thing is done through slides, but somewhere in between. And this is like in line with the spirit of this course, that this is neither a very fundamental like core course for a particular department, nor it is a fully research course. So it is a sort of a bridge between a core course and a full research level course, and our teaching style will also be commensurating with that. So to begin with, we will discuss about the general philosophy of conservation. So like the general philosophy of conservation, when we apply, we may use it for conservation of mass, we may use it for conservation of momentum, we may use it for conservation of energy, we may use it for conservation of species, we may use it for whatever conservation, but generally in fluid mechanics we tend to use an Eulerian approach. That means we try to identify a control volume which occupies a fixed region in space across which mass can flow, energy can flow, momentum can be transported. So this control volume, across that something goes in, something comes out, there is some change within the control volume, and the net change within the control volume is nothing but in minus out plus generated. So the total change in the control volume, for example let us say if there is a mass that comes in, whatever mass comes in, if the same mass goes out then there is no change, but let us say that because of chemical reaction there is some species which is generated. So whatever has come in minus whatever has gone out plus whatever species that has been generated because of reaction may be the total change in the mass of the species that is under consideration. So that is a basic principle of species conservation. So this kind of conservation principle you can use for any particular scenario. Now what is the important consideration that you have to keep in mind in fluid mechanics? The important consideration is that all our basic laws of fluid mechanics are in general described, I should say basic laws of mechanics, classical mechanics, I mean forget about fluid mechanics, are described on the basis of a Lagrangian point of view. That is, you identify fixed particles or fixed mass and write equations, maybe equations of motion or whatever, for that identified mass, which is called as a control mass system. On the other hand, in fluid mechanics it is convenient to describe the scenario in terms of a control volume. That means an identified region across which mass and energy can flow, and the reason is as follows: if you have a specified region in space which is your control volume, let us say this is your control volume. Now you can sit with a camera and target to the control volume and see whatever changes are taking place across that. So something comes in and something goes out, some change is taking place within that, you are not bothering yourself about where from that something has come, where will that something go. So you are not tracking individual particles, and tracking individual particles in fluid mechanics is a very difficult job, because fluid elements are continuously deforming during motion. So that it is very difficult to track individual fluid particles. So what instead you do, that you write your equations of change with respect to this control volume, although the basic laws of mechanics are described for a control system, control mass system. So there must be a transformation, that will try to transform from a control mass system to a control volume system approach, so that a control volume based approach, so that you can write your equations of motion with respect to control volume rather than with respect to a control mass system. It is not just true for equation of motion, but maybe even the first law of thermodynamics and so on. So different conservation equations. So that is achieved by realizing a transformation through something which is called as Reynolds transport theorem. So in Reynolds transport theorem, what we are essentially interested in is that we have a control mass system. So we have a Lagrangian approach and we have a control volume concept which is the Eulerian approach. So we want to write a mathematical transformation that transforms the Lagrangian approach to the Eulerian approach. So to understand how this theorem is applied, if you look into this diagram which is there in the slide, if you look into this diagram, let us look into this diagram very carefully. You have this pink colored region, I mean this total contour is the system at time t. So the system at time t is the region 1 plus the region 2, together the pink colored region is the system at time t. On the other hand, the region with the sky blue color is the configuration of the system at time t plus delta t. If delta t is small, the differences in the configuration, the differences are not that large, but we have sort of magnified it in the diagram, we have magnified this in the diagram to sort of make the system configurations distinctly looking in the figure at time t and t plus delta t. So let us say that capital N is an extensive property of the system. Extensive property means a property that depends on the extent of the system. So, you can write n at time t. So, if you get back to the slide, n at time t is a combination of n at 1 at time t and n at 2 at time t, right, because at time t the zone is zone 1 plus zone 2, alright. Similarly, you have n at t plus delta t is equal to n 2 at t plus delta t plus n 3 at t plus delta t, okay. So, we are interested in finding out what is dn dt of the system, dn dt of the system. So, dn dt of the system is what? By definition of the derivative, it is limit as delta t tends to 0 n t plus delta t minus n t divided by delta t, that is the definition of dn dt. Now, what is n at t plus delta t? N at t plus delta t, so let us write this in the board maybe to explain it better. So, we have a configuration, so we have this is 1, this is 2 and this is 3. So, n at t plus delta t is n 2 at t plus delta t plus n 3 at t plus delta t, and n at t is n 1 t plus n 2 t. So, our calculation is dn dt, that is limit as delta t tends to 0 n t plus delta t minus n t by delta t. So, we will see that at 2 you have a change in n because of the change in property at 2 with time. So, you have limit as delta t tends to 0 n t plus n 2 t plus delta t minus n 2 t divided by delta t, plus now you have certain adjusting terms. What are the adjusting terms? This is a term which is a positive plus term and this is a term which is a minus term, right. So, now if you divide this by delta t and take the limit as delta t tends to 0, then what is that? That is the property that is transported across 3. So, that is nothing but rate of outflow of the property. Similarly, when you write this one, what is this? In the limit as delta t tends to 0, this is inflow of the property. Inflow outflow with respect to what? With respect to this common region which represents the so called control volume. So, because why this region represents the control volume? Because as delta t tends to 0, right, this is the region which is that region in space across which if you like focus your attention, then you can see that this is inflow and this is outflow. So, this is like an identified, this is the region in space which you can identify across which you can study the transport. So, this is rate of outflow minus inflow, outflow minus inflow of the property, okay. Now, let us think about the first term. let us think about the first term. So, what is this? This is the rate of change of n with respect to time within the control volume, right. So, why we write it as partial derivative of n with respect to time? We write it as partial derivative of n with respect to time because at a fixed location we are studying the change with respect to time, that is why partial derivative with respect to time. Now the next question will be that how to express the outflow minus inflow. So let us say that, let us identify a region on the control volume and see that how we can express the outflow. Let us say this is a small area dA. Now an area has a orientation. How do you describe the orientation of an area? You describe the orientation of an area by its outward unit normal vector. So let us say that eta cap is a unit vector in the normal direction of dA. So what is the volume flow rate across dA? The normal component of velocity times the area dA. So if v is the velocity, then we have v dot eta dA, okay. So this is the volume flow rate. This multiplied by rho is the mass flow rate, and let us say that small n is the property per unit mass, that is small n is capital N per unit mass. So if you multiply that with small n, this is the total outflow of the property integrated over the control surface. CS means control surface, surface which is bounding the control volume. So then I mean as an alternative notation, many times this can be written as a vector dA, right. Either you write is as the normal vector times the scalar area, or you write it as a area vector itself. I mean these are two alternative ways of looking into it. So this is outflow. Now how do you write inflow? So when you consider inflow, let us consider an area here. Now here the normal direction is like this, and for the fluid entering the control volume the velocity is like this. So what is the most important demarcating factor between this scenario outflow and the inflow scenario? So if you consider the dot product of V with eta, here the dot product itself is positive, and by looking into this figure you can understand that here the dot product will be negative. That means when we say outflow minus inflow, we do not have to use a minus sign, the dot product positive will automatically indicate outflow and the dot product negative will automatically indicate inflow. So for the outflow minus inflow we can write together this common term integral of rho v dot dA into n, small n, where the control surface, some part of the control surface may be inflow, some part of the control surface may be outflow, some other part may be neither inflow nor outflow, okay. Now we have to keep in mind, or we have to pay a little bit of attention to what is this V. So, this V we have to remember that this V is nothing but the fluid velocity, but to be more precise, velocity of the fluid relative to the control volume. Let us say that the control volume is a tank, just as an example. Let us say that the tank is moving towards the right at a speed of 1 meter per second, and water is also moving towards the right at a speed of 1 meter per second. Then what is the rate at which water is coming out of the tank? That rate is 0, because tank is also moving, water is also moving in the same way. So, relative to the tank, no water is moving out. So, to get the net flow, it is important to understand that the velocity has to be relative velocity, VR, velocity of the flow relative to the control volume. This relative velocity is same as the absolute velocity when the control volume is stationary, when the control volume is not moving. Otherwise, we have to be careful about this. Okay. So, when you write this VR dot dA n, then it completes the description of this term. Now, what about this small n, capital N? So, if you take a small volume within the control volume of dV, because velocity sometimes we use V, so we are just using a little bit of different symbol to indicate volume. So, what is the mass of this element? Rho dV, and small n is the property per unit mass. So, this integrated over the control volume is the total n. So, we have described this, and in the left hand side what is dN dt is dN dt of the system. So, with this basic understanding, let us now go into the slides to complete the algebra. So, you can see here that we have these two terms, this is the first term and this is the net outflow minus inflow term. So, these two terms if you write mathematically, then you can express the total rate of change with respect to the system in terms of rate of change with respect to the control volume, and you can see that there is a correction term. This correction term is because of outflow minus inflow. So, if there is no flow taking place across the control volume, of course the control volume is as good as a control system, and there is control mass system, and there is no difference or no change taking place across the control volume. Now, this particular expression which is highlighted here relates the rate of change with respect to a system with the rate of change within a control volume, and that is known as Reynolds transport theorem. So, Reynolds transport theorem is a very powerful theorem, and we will use this Reynolds transport theorem to derive various governing equations. So, to do that we will first go to the case of conservation of mass. So, conservation of mass is a very basic requirement that needs to be fulfilled for any problem that we undertake, no matter with whether it is microfluidics, nanofluidics, gigafluidics, whatever fluidics you call, I mean it has to be satisfying the conservation of mass. So, for conservation of mass we